has uploaded the latest notebook for his exercises to Slack. Also, Dragan, let us know when you want to conduct that poll that we
I'll let you know. Yeah. Well, let's see. Do we have majority? Oh, I see. I don't see how many. I don't see how many participants we have now versus.
We have 95 right now, and it's going up fast.
Okay, let's wait. I'll sometime after I start, I'll ask you. I won't forget. I hope. Yeah. All right. So I think I will start. Let me see. Hide floating. Okay. I hope everybody can see the screen and hear me. I will assume that's the case. Today we have day 2 of my lectures. Like I said yesterday, basic cosmology combined with numerical exercises, with particular emphasis on things that are useful. And one thing I forgot to say yesterday that happened sometime during the day is I've posted, or Tiago's posted for me, a set of typewritten lecture notes. You can search for quote unquote lecture notes for the whole week in the program. So it's one set of notes that accompanies my lectures. It has some more material in the lectures. It's some extra stuff, but everything that I'm going to talk about is more or less contained in those notes. So you can use those at your leisure. It's just one single set posted in addition to the slides, in addition to numerical exercises. Well, let me start today with no further ado, because I'd like to get to numerical maybe in half an hour. Yesterday, we discussed the power spectrum, dimensionless power spectrum K cubed P of K, and we happily coded it up from scratch. It's a power law in K, where you have to take note of the units, in particular of K pivot, which is conventionally given in unusual units of just megaparsecs inverse. Has some prefactors and a Hubble constant, and then most importantly has a growth function that looks like this, squared, and has a transfer function squared. And then the nonlinear part we ignored. That's just a catch-all for any kind of nonlinear prescription, which can also be coded up, and I may even provide it at the end, but it's just a little bit beyond the scope of what we have time for. Notice if I were just giving theory lecture, I would say this is d of a squared. But it's not exactly d of a, it's a g of a, which, remember, differs from that d of a term by something like 0.76 by little g evaluated today. So it's 0.76 squared of what d of a would be. Okay, so that we did yesterday, and I think I flashed this picture of biggest, some of the biggest and best known surveys, all of which are large-scale structure and all of which are probing dark matter and dark energy. I'm going to show a couple of slides from Tim Eifler, who is a cosmologist very much involved in these surveys. And you can see there's so much to say about them. I could spend an hour or more talking about them, but I won't, because I think it's more useful to work on concrete things. So these are some of the past surveys. CFHT legacy survey was really big, started when I was in grad school, and in 2013, maybe 15, they had big releases. Cosmos is a really small but really deep survey on which you can practice photometric ratchets, things like that. DLS is an early weak lensing survey. These are roughly present day surveys. They're all quite powerful, and you can see their relative sizes in square degrees. And then the future is really amazing. There are other ones here as well. These are mainly the ones that Tim Eifler is involved in, which are some of the biggest ones: Euclid, WFIRST, and LSST. WFIRST is now called the Roman Space Telescope, and LSST is called the Rubin Observatory. So that's just an overview, and area here is only one thing, but they are actually the newer surveys are better along multiple axes, and so they're really much more powerful than the previous ones, which makes control of systematics and even control of theory much more important than it used to be. And if anyone has any questions about any of these surveys, I can answer. I'm not a super duper expert, but I probably know them at the level I can answer questions. Let me see if I skipped anything. Yeah, so some of the most important probes, this is a slide I made many years ago, but this is roughly redshift coverage at the present time then and in the future, along with this, of some of the key probes. These are some of the key cosmological probes of dark energy and cosmology in general. So cosmic microwave background is probably the most famous cosmic microwave background anisotropies. Then you can count clusters of galaxies. That's something we'll do today in our numerical exercises. Sorry, that's this one. You can count clusters of galaxies. you can just have measurements of the power spectrum, galaxy clustering. If there's time in the next few days, I can say some more things about it. There's weak gravitational lensing, we'll cover it very briefly. BAO, we'll barely have time to talk about it. And type 1a supernovae, which also, some of these things, you know, they will take time to discuss, but maybe very briefly, I'll discuss a few of them. And here's a kind of a nice picture of how you have the photons from the sky, right? And you also have some theory. Where do they meet? So here's, you know, you can write down the power spectrum like we did and code it up in Python. But a more general, arguably more powerful way is to do that, but then to run an n-body simulation. And then you also have not only dark matter, you can add some galaxies somehow to that simulation and calculate the power spectrum from that simulation for a given cosmological model. On the other hand, you start from your observations from sky images, you decompose that somehow, and you measure the power spectrum of galaxies, say in your sky, and then you compare the two. You compare, this is your theory branch on the bottom, and this is your experiment branch, observational branch on the bottom. They meet to the power spectrum. Power spectrum or its derivatives, you know, weak lensing power spectrum, or occasionally distances measured by supernovae. They are the meeting place between theory and experiment. So this is very important. Power spectrum is a key quantity in cosmology. I think I said it last time, P of K. Most large-scale structures probes effectively probe the power spectrum, sometimes, you know, or its derivatives. Inflation predicts it, of course. The whole last week was about that. So it's a great meeting place. And as I said yesterday, in the Gaussian limit, of course, it contains all information. Power spectrum is really key, which is why we are spending time on it. And then all these other derivatives you can do, you know, but it's important to be comfortable with the power spectrum. This is a slide that Pedro Ferreira showed in the beginning. I think he was the one who showed that. And this is, I don't know if he in how much detail he went to explain it. This is P of K as a function of K. Black line is theory. This is from the Planck overview paper by Zaldariaga and Tegmark, I believe, are the first who had an early version of this plot. These are effective measurements of the power spectrum. Now you say to yourself, well, okay, I know that Sloan Digital Sky Survey, maybe BOSS, they measure galaxy clustering, so they literally measure these things. But these other things, cosmic shear, and certainly the Planck anisotropy, they don't measure clustering of galaxies. They measure some other quantity. In the case of the CMB, it's the angular power spectrum of TT, EE, etc. It turns out you can deconvolve, you can undo typically observables in these other, like in CMB or weak lensing, integral P of K, DL and K, or something, okay? So you can kind of undo that. You can't really take derivative of the observable, but there are fancy ways to undo it in order to say what P of K did they really measure. And you can see they have measurements. Some of them are better than others. And of course, most measurements are in very good agreement with theory. Okay, so that's where you place measurements from a variety of probes on the power spectrum. Can you do the same thing with type 1a supernova? You cannot, because they fundamentally do not measure clustering. They don't measure power spectrum, they measure distances. So this can be done only for quantities that measure clustering of galaxies, CMB hot and cold spots, others kinds of things. Okay, that's good. Now, I am going to talk a little bit about, let's see, so let me talk about smooth overdensity. So I'm shifting gears slightly. So it turns out if you think about the imagine you say, okay, what is really delta? If you think about the raw quantity of delta, this delta here, that's not smooth. Delta over rho, if you go around the universe and ask, let me look at this point in space, let me look at this point, let me look at this. You are talking about empty, 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 empty proton. You know, you hit the proton, you hit some particle, and then you go from delta of -1, -1, -1 with empty space to infinity, right, or very high. So you got these huge, enormous fluctuations if you think about it. You can also thinking about going on the beach and looking under a microscope in the sand and finding empty space, empty space, empty space, even maybe with an atom empty space and hitting something. So it's clear that you have to smooth. You have to smooth delta in order to meaningfully talk about observability. So you can think about that and you realize you have to smooth. Just like our eye smoothies on the beach and kind of sees some general features, just like here you have the smooth. Smoothing is obtained by convolution. I meant to note this here. This is a convolution. So convolution is, if I had a blackboard, I would illustrate this better, but I don't. So I'm just gonna wave my hands. When you see a function of r minus r prime, the smoothing function times your function of r prime dr prime, that's the convolution operation. And it turns out that smoothing is convolution. Okay, so convolution is that scary word that I remember my roommate in college was doing engineering. They were doing convolution. I had no idea. Much later, when I did cosmology, I learned it's just smoothing. Smoothing is obtained by cosmolution, and you can think about how this works, the smoothing window. The smoothing window we apply, there are other choices. Typically, we use the top hat. It's called top hat smoothing windows, which is flat out to radius r and then goes to 0. Because convolution in real space is multiplication in Fourier space, here's multiplication, you need a Fourier transform of the top hat window. And here's where our headache kicks in. Because our in real space choice for W, I don't have a picture unfortunately, is just a top hat. So it's flat at say 1 and then goes to 0. It's flat with r between 0 and little r between 0 and capital R, and then it goes to 0. That sharp function in Fourier space does what? It oscillates like crazy. So it looks like this. This combination in the numerator is just a spherical Basel function of the first kind. It's a like crazy oscillating function when kr is much bigger than 1. So integrating this is a pain, and we're going to do that today in our numerical exercise. Fortunately, Python is high level enough that if you just say, hey, please integrate this for me, it'll just work out of the box. But it is a very wiggly function, so sometimes you have to pay attention. Anyway, so in Fourier space, this is simple. And then oftentimes, remember, we want the correlation function, which is like delta delta. And delta delta is what delta delta used to be times w squared. So remember that zero leg correlation function that was integral of delta squared dln k? Now it's that times the window function squared. So the window function is just there because of smoothing. And if you're going to measure anything, this is the kind of thing you want. You need to have this window function there. Otherwise, for example, you can easily show that this integral diverges. And I think it's both infrared and ultraviolet divergence, if I remember correctly. It's very badly divergent, but it won't be once you do the smoothing function. So again, some people sometimes choose the Gaussian for W, in which case the Fourier component is also Gaussian, but unfortunately, the convention in the field, and this convention that this be top hat, which means that the Fourier part is the spherical Basel function. Anyway, now we come to the expression with this psi of 0, we just rename it, and people call it sigma squared. So this is the amplitude of mass fluctuation squared, smooth on scale r. So this is a very important quantity to understand intuitively, and then we're going to code it up later today. Imagine you're going around the universe with a cookie cutter, the size r, except cookie cutter is 3-dimensional, it's not 2-dimensional. So you go around with volumes of spheres of size r, and you enclose one chunk. That sphere can be 10 megaparsecs or 1 megaparsec or any size. So you enclose volumes, and you say empty space, empty space, empty space, empty space. Oh, I enclose the galaxy or something, right? So fluctuations. So you go around, you do statistics of that, and you almost build like a histogram. You say, what was the variance? What was the variation of this process? That's what this is measuring. It's really variance, right? Remember, this was a variance. It's a zero leg correlation function. This is also variance. So it's so if you think going back to one of those n-body pictures that hang everywhere on walls and you can see them, imagine going with a cookie cutter, imagine taking a big volume. As you go around an average, most of the time you find the same amount of fluctuation, right? So you say, so this quantity will be small if r is big. But imagine if you pick a small volume, small r, then you're going to have empty space, empty space, empty space. Oh, I hit a galaxy, I hit a cluster. So you're going to have a lot of fluctuation. And so sigma is going to be large. So for small r, this is large. For large r, this is small. This is already logical. You could do this. You don't need cosmology to do this. You could have done this for any process for, pebbles on the beach or anything. Okay, but this is intuitive understanding of what this is. It's very important because this is one of the key quantities in cosmology. This is called amplitude of mass fluctuations. And in this case, it's squared. So this is that amplitude mass fluctuations. Its special case when capital R is for historical reasons 8 in our favorite units, h-inverse megaparsecs. So 8 h-inverse megaparsecs at redshift of 0. This depends on z because you have a choice what z you put in for the power spectrum. That's called sigma 8. This is one of the most famous quantities in cosmology. It's kind of unintuitive. So if you're a graduate student, it takes you like a year or two. It took me at least to figure out what people are talking about. Everybody talks about this because it's historical. It measures fluctuations in the universe roughly on the scales of galaxy clusters. Now, notice that sigma 8 is a kind of sigma, right? Sigma squared is proportional to the power spectrum, which is proportional to amplitude of the power spectrum. So you could say, why not just talk about amplitude, capital A, of this power spectrum? You could. It contains similar information, but historically, people have gone with sigma 8. Why not sigma 9? Why not sigma 7? Well, because it's historical, okay? So sigma 8 was historically, and this is a dimensionless number. Well, notice everything here is dimensionless. Every term is dimensionless, so this is dimensionless. It happens to be a ballpark unity. This was like Hubble constant that was argued to be 50 or 100. For a long time, sigma 8 was either 0.6 or 1. People argued. And then eventually, this was like Hubble constant. Eventually, it settled like Hubble constant somewhere in the middle, but also like Hubble constant. Now there's some tension. Certain kinds of measurement favor 0.77 or so, or 78, and certain kind of measurements favor 0.80 something. And there's a tension between these two, which is not 5 sigma, but it's something like 3 sigma. Okay, so that's the story of sigma and sigma 8. Let me see. So maybe let me look at the chat briefly. Do we have any questions? Oh, people are talking about something else. Yes, Lyman Alpha is also a probe. I only mentioned tip of the iceberg. There are many probes, and sorry, Lyman Alpha people, it got left out of my slide. It's also a probe of clustering, of certain kind of clustering. Yes, Lyman Alpha. There's photometry and spectroscopy. Yes. Specific shape, this is a kind of convention. If you're doing smoothing, you have a choice of the smoothing function, and because you still haven't connected to observable quantities, so you still have a choice of the window, and people have agreed on the top hat window. You could have done the whole thing with another smoothing window. You would have had to redo your connection of the data. But yes, R is a parameter describing the window size. Yes, yes, and that's right. No, there's no better or worse window. This is purely a convention. Convention is the red light, don't cross the street, green light, cross the street, right? It's unimportant which one is which, as long as people agree. So this is the same. It's just kind of mathematical procedure of smoothing. We still haven't connected to data. So in other words, had you chosen another window, maybe you would have had a slightly different coefficient in your final equations connecting your data, right? So it's just pure convention. There's no depth in the choice of W. Yeah, why chose historical is 8. Yeah, you can pick any R, but I'm talking about sigma 8, which is for R of 8. That's famous. And the question about n-body is not really relevant to this. So let me just move on and maybe leave it for later. Okay. And all right, so that's that. So let's say you do have a good chunk of large-scale structure. What can you do? You have I give you 100 million galaxies of some survey. Here's a positions in 3 dimensions, ideally, of 100 million galaxies. It's a little dirtier than that usually in a photometric survey. You don't get 3 dimensions. But what can you do? You have some choices. You can count them, and that's the simplest thing. Let me just count them. You can't count galaxies because it's too complicated to connect to theory. To think about that, think about counting planets and connecting to fundamental theory. That would be impossible, right? Connect string theory to a number of planets. That's too hard. Maybe in year 3000 we'll have that. But galaxies are also just too complicated. But clusters of galaxies are just barely doable. And we'll do today in our exercises. We'll be coding up. So you can count clusters of galaxies. We're going to do that today. You can, of course, do 2-point correlation function in the real space or Fourier space. And that's been a workhorse in cosmology, as I said. Then you can do more exotic things. You can do bispectrum. That's cool. That's really good to do, especially on nonlinear scales. It gives you extra information. It's hard to theoretically predict, hard to measure. So it's a tough job, but a lot of people are working on that. You can calculate alternative measures. This is exotica. You can do count peaks. You can measure topology. You can have other measures of logical structure. It's a really good thing to do. Some of it has the same information as a dew-point function. Some of it has new information than dew-point function. And that's, voids and counting empty spaces. Void has been a big topic. And then finally, this is a catch-all for complication. You can study internal structure of galaxies and star formation, etc. But that's also tough to connect to fundamental theory. Say, for example, you want to get insight on inflationary parameters. So these are your choices, what you can do. Number 2 is the workhorse by far. And then after that follows some combination of number 1, number 3, and number 4 is behind still. All right. So we talked about measuring. So here's 100 million galaxies, or maybe 100,000, not to overwhelm you. Give me the power spectrum, please, or give me the correlation function. Here's the simplest way to do it. It's called a Peebles and Hauser in 1974. You can see a lot of things in cosmology are named after Peebles, who won Nobel Prize like last year, I think, who is maybe a year before that, who is the most famous living cosmologist, I think it's fair to say. So they said the following. This is a definition of the two-point correlation function. It's excess probability for clustering. So let me do the following. Let me count for some distance r in some window. Say, so for example, if r is 5 megaparsecs in a window from 4 to 6 megaparsecs. Let me count the number of pairs of galaxies, all pairs, and this is number of pairs that are between 4 and 6 megaparsecs. Let me take a completely random distribution of galaxies and count the number of pairs in that random distribution between 4 and 6 megaparsecs. And I just normalize in case one of these catalogs is bigger than the other. This is just normalization to account for that. Let me subtract 1. So if D were like R, DD over RR would be 1, and that would be 0. That would be 0 clustering. And then if there's more clustering at some distance, DD, number of pairs is going to be bigger than RR number of pairs. I'm going to get positive correlation function, vice versa, negative. This is a very simple thing to do. You already have the D catalog. You just have to generate random catalog, generate random positions, random points in three-dimensional space, and you have to run this. Very easy to do. It's brilliant. It's really easy. Turns out statistical properties of this are not great. You do better by using this Landisla Estimator. If you do a similar thing, except you add a term that's -2, and you take each galaxy in the data and compare that to positions of random points in a random catalog, and you count the number of those pairs as well, separated the distance r. And it turns out if you do this kind of slightly more complicated thing, which also in limiting cases has a logical expected answer, you do better. So this is called Landisla Estimator. This is a research level formula you can apply, and it's as easy to run as it looks. These are n-squared processes, a bit slow. You can speed them up if you get clever. All right, I'm only going to have time for one of these extensions. And that extension is going to be, let me just look at this. Yeah, 2020 did just pass. I agree with that. It was Nobel Prize in 2019 for Peebles. Yes, indeed. Yes, that I just realized as I was speaking. I only have for one of these extensions, and like I said, I'm breezing through this a little bit. Fabian already talked about peak background split. He had something about this. You can look at the slides. I have a basic derivation of that in my notes as well, in the typewritten notes. I want to do the press trajectory quickly and then code it up on the computer. So here's the so-called mass function. Mass function is the number of objects per mass. In the log, this is a log space, and you see it falls like a rock. These are actual measurements, and this is theory. So it turns out that clusters, as I mentioned, are just barely linear. They are delta rho over rho on the scale of clusters is ballpark unity. Galaxies are already basically nonlinear. So it turns out, as I said moments ago, that there's no hope of counting galaxies and comparing to fundamental theory, but there is just barely hope in counting clusters. So the question is, Can we predict this fact that, so these are, you can see typically the rule of thumb is 10 to the 12 solar masses is a galaxy. I'm a theorist, so this is just very approximate. 10 to the 12 solar masses is a galaxy. 10 to the 13 is, I guess, a group of galaxies. 10 to the 14 solar masses is a solid cluster, and 10 to the 15 is like the most massive cluster. There are no 10 to the 16 solar mass clusters in the universe, and the most massive one is, you know, ballpark 10 to the 15 or 2 times that. Okay, so is there hope from scratch, you know, deriving this? Of course, you can run numerical simulations and build up kind of the histogram and learn the distribution of this mass function from there. But is there, and you can see here that as you go to clusters form last, so if you go to higher redshift clusters, there were fewer things, there are fewer massive objects, and then as you go to present time, there are more of them. I'm going to be here a little bit lazy, by the way. I'm interchangeably using the terms halos and clusters. Halos, theory typically predicts halo distribution and maybe properties. Halos, you think of halos of dark matter. Clusters, of course, things that shine. I'm just going to mix them up here. I don't think it's super important. Okay, so here's a brilliant Preston-Schechter. This is one of the most famous arguments in cosmology, one that fits on one single slide and that you can do with freshman level mathematics. They said the following: a region of radius r has mass 4 pi thirds r cubed rho m, where rho m is density, mass density. And Fabian talked about critical density for collapse of 1.686, this thing number that looks precise. It's just a number you get from spherical collapse model. So very, very simple model that, as Fabian talked, you know, you can predict everything. So then Preston-Schechter say, let's calculate the fraction of collapsed objects. What's a fraction of collapsed objects? They say it's probability of some over density delta, d delta, where delta goes from this number to infinity. Okay, they just say they're going to add them all up, and you're going to, you know, in the Gaussian limit, this is just a Gaussian. This is e to the minus delta squared. So if the distribution is Gaussian, this is a Gaussian. You integrate that, and you get error function. That's integral of the Gaussian. It's the error function of where nu is this peak height. It's delta c divided by sigma. So this is where sigma of r plays a role. Sigma entered here as the variance of delta, right? This is where sigma enters originally. So far you're already saying, why should this ever hold? Spherical collapse is too simple of a model. This, I don't know, this is Gaussian. Okay, already there are a bunch of suspicions. So now they say the mass function, which is d number density d log mass. So this is number density log mass times d log mass. So number density is, and you just kind of follow the units here, it's the part of this fraction that's in that interval times the ln interval. And then you just have to sort of convert the units to get units of number density, which is mass density divided by mass. So this is kilograms per meter cubed divided by kilograms is going to give you numbers per meter cubed. Okay. So now you got everything, and you know all you need to take is the derivative of the error function. Derivative of the error function is again some kind of Gaussian. But also what gets derived is this sigma. Sigma depends on cosmology, it gets derived. So you just take a derivative of this thing and plug it into here. You get the Preston-Schechter mass function. And then goes one of the most famous sleight of hand arguments in the history of cosmology, probably. They say, okay, that was good. But, you know, we only counted over densities. We forgot to count under densities. To me, at least, it doesn't immediately make sense. Well, let's multiply by a factor of 2. So they just take that, multiply by 2, and this is their answer. So this is, in other words, this expression multiplied by a factor of 2. Now, the completely amazing thing about this is that this mass function with these 15 approximations, 14 of which are completely suspicious, actually works really well. Up until recently, up until when I was in school, it was, you could do it for research. You could run your codes with a Preston-Schechter mass function. Nowadays, it's not quite accurate. It's only accurate at like 10 or 20% or 30%. So people use much more modern mass functions. But nevertheless, it's completely remarkable that something like that works. Why it works, I don't believe there's an easy answer. Fabian talked about excursion set theory, and excursion set theory explains a lot of the reasons why this kind of thing should work. But there's no, easy silver bullet to why such a rough approximation works at all. So here, what do you need to do? You need to, if you're interested in number of objects per unit log mass in some cosmological model, all you need to do, you need raw matter, you need omega matter for this raw matter. Delta C is a constant, and all you need is a sigma. Sigma comes here, here, and here. And if you have sigma, you have everything for the pressure mass function. So the fact that, this is not some complicated function of 6 fundamental cosmological parameters. This is a function of a function that still depends on all cosmological parameters, but it's only one sigma. So if whatever your cosmological parameter, cosmological model is, as long as it's within reason, it's not one of the models that Pedro Ferreira mentioned in his lectures. Okay, it's some variant of smooth dark energy models with GR. If you tell me sigma, I can tell you the mass function if I assume it's pressure. Okay, so this is called universal. The fact that it only predicts, you hear about universality, that means it only depends on sigma. More careful studies, in particular this one and the ones later, show that there is nothing fundamental in the universe. It's not a theorem of the universe that this has to be universal, but so universality breaks if you want a really accurate mass function, say from simulations. But if you're satisfied with this accuracy, they are universal. And this was really kind of one of the most famous arguments in derivations cosmology. You saw it fits on one slide. It's also in my lecture notes. Let me see if I have any other slides here. Right, so let me first look at the chat. You can count galaxies, but how can you compare them to fundamental theory? Imagine a completely crazy example. Count how much grains of sand are there in the world, and try to connect that to fundamental theory. It is true, it all did come from fundamental theory, but it's so far removed from it that counting it, or counting number of planets. So in the same way, galaxies also, you can count them, but there is no solid theoretical prediction of how many we expect in some volume. Yes, and Matteo people have agreed on this. Okay, so I think that's good for these. So maybe, Raul, do you want to, I'm just, before I move on, let me just get that, if you don't mind running that poll. So I have a poll, it's asking the following question. I just want to collect data here and return it to Google. No, just kidding, just for our own benefit. I'm curious whether you've had A, lots of programming experience, B, some programming experience, C, only very little programming experience, or D, no programming experience. So
Dragan, let me just check. Tiago, can you run the enquete right now? Okay, so guys, everybody is going to see kind of a window appearing. I hope you guys are seeing this.
It's appearing, yes.
All right.
Significant, some.
All right.
Oh, none.
Well, at this point, none cannot be anymore, right? After the exercise is done.
Up until a few days ago, yes. Yeah. Okay, so we have, okay, so we have a very solid here. None is okay, by the way. It's a perfectly valid answer. We've had grad students who came with only email and Facebook was their computer knowledge, and they ended up writing computational theses, computational cosmology theses. So that's happened, but it's good to see a lot of people have decent experience, could be better. Honestly, that's a category in which I feel I belong to. It's okay, it could be better, but okay, thank you very much. Thank you. That's good to know. So that that answers this question and helps. So we have so what are we going to do next? We are going to ask, this is the real research question. This could be even your advisor could ask you this for the first mini research project to calculate this. Say you have some survey, it's going to turn out to be 5,000 square degrees. And let's say it covers some redshift range. What's the total number of objects, say, above some mass? It's going to be 10 to the 14 solar masses for now, right? It shouldn't be too low. It should be clusters of galaxies, right? Because that's something we can compare to actual observations. So say I have, for example, dark energy survey. I count, say I can detect them well, say I can measure their mass accurately, which is really hard. What's their number? So we're going to do the theory expectations. So their number per unit angle per redshift is number density. So number is number density times volume, right? Imagine DLM cancels out, right? So number is number density times volume. And then I have per d omega per dz that also follows on the right hand side. So that works out. And then I only rewrite this equation as d and DLNM. And then I have dv d omega dz is r squared over h. R is a comoving distance. The reason this holds is if you think about the volume element, it's r squared dr d solid angle. And when I divide by this, d omega cancels out. And dr dz from the formula for r of z, dr dz is just 1 over h, right? Because dr is integral dz over h. So dr dz is 1 over h. So this is a very useful formula. This term is going to be two very simple functions that we coded up already. And this is an integral we have to do. But what I really need here is the mass function, which is going to be Press-Injector for us. Okay. And I'm not going to have a chance to talk about this. So I'm going to stop this sharing and start on our code. Again, you can open like yesterday, you can follow along with me. You can try to type, and I'm going to spend some time on it. We have some time to work on it. Share screen. Okay. All right. So you should all be able to see this should be called exercise 2, by the way. You should be able to see my code, and hopefully you can connect there and follow. If not, you can just see what I'm doing and try some later. So I copied a lot of stuff we did yesterday. First of all, I run this. I'm going to do this in a pedestrian way. I run the box here, and it's going to be a little slow. And then it's going to hopefully it'll ask me in a moment to, as I said, this chunk here is just to make plots look pretty. So don't worry about too much about it. Then let's see, when that completes, I'll see, maybe it wants me already to. Okay, so I hopefully that completed. Then I run this, is just cosmological parameters that I defined yesterday. These are the distance functions I defined yesterday. And then the growth function, I'm just going to run it. We had the growth function yesterday. This is little g, a little g, and then dA. So this is the Carroll, Preston, Turner growth function, just for simplicity. And then the spot where I also skip and go to BBKS transfer function because it's easy. We coded it up yesterday. And finally, the power spectrum we had yesterday. We had this delta squared power spectrum. So this is dimensionless power spectrum. It's k cubed p of k of 2 pi squared. So I think I ran all of that. Now I ask you here, here's what we have to code up. It's the amplitude of mass fluctuation squared. We have to do this integral. What you'll find useful is that I imported here SciPy routines, and the Bessel function, spherical Bessel function of the first kind is this expression. So start here, put in an integrand of this function, put it in here. And that'll allow me a chance to take a breather. Then the sigma itself, I did it for you. I'm going to lead you through it in a moment, and then I'll tell you to report what you get for sigma 8. But first, let me take a breather here. First, do this. And if you have any questions, type in chat. Oh, zoom in. Yeah. I can zoom in. Yes, I can. Let me see if I can zoom in. I don't know if there's a way to zoom in, but if I do this, I think hopefully you see a little bit bigger picture now, right? All right, so let me see. All right, so there's some questions. Yep, so I'm going to try this. So let me see. I'm just trying to get something going here. I'm trying to see it in my over there, but it's not working. So here, what I will have is just a second. Let me see. All right. Well, I can't see my other screen, unfortunately, in this real time. Let me see if I can. I didn't remember to do this in time. Okay, let me try again. I can just try this and see. So that's going to be something like. All right, I don't quite have it here, but I will need that function. So I need the power spectrum that I believe takes all the same arguments, right? So like delta squared is equal to, I think this thing is completing for me. Delta squared equal linear of, and then all of these arguments. Z, I don't know, this is Z, K, A, H naught, omega matter, omega B, and NS. So it is A, K at 0.05. Right. Let me see if I have it here. Just give me just one moment. Let me do something here. I need to. Okay. In the meantime, you can work on that in those boxes below. Well, this is refusing. So let me, okay, I didn't do this in time. Never mind. Let me go back here. Let me just approximate this and then I will. All right. So this is delta squared and then I need to multiply that. So I basically need to just return, follow this times delta squared times this quantity 3 times, and what is it called? SP dot spherical JN odd 1 and x divided by, really that's x, that quantity squared, times, so that's the integrand. And then of course, key thing is that x is equal to k times r. So this is, this really should have been called capital R. I don't know why I call it small r. It's better to call it capital R. Doesn't matter. And then, of course, what is k? You're given log k. So k is just going to be 10 to the power of log of 10k. So notice a few things. First of all, I'm giving memorable names to all the variables. And then you can see that I'm going to be integrating this expression you want to integrate in log k, right? Which is why you want to pass maybe log base 10 of k. And then 10 to that is just k. You'll need k because kr is going to be this argument, okay? And so I think this takes care of my integrand. Next, I need to integrate it. And it's the only thing here is that this is where I'd love to see my solutions, because I think I'm just gonna do, maybe I'll switch to them, because this thing is integrating in I have base 10 and base e logarithms, so I have to worry about them, okay? So that's where I have to worry about. But other than that, let me look at the chat if there are any questions, and let me, yes, you do have to be careful about log base 10 and k, and you also have to be careful about, let me just give this one more chance here. This is the first time I'm doing numerical exercises this extensive, so there are some growing pains. But if I try upload now, and this didn't upload really, so. Oh, I see it didn't. Okay, now it's going to work. Okay. Okay, upload. All right, I may have to do without it. So it's a little bit hard when I can see my own solutions. And so that means I have to be coding up in real time. But this gives you, this is k, this is integrated so you go integrate this expression from say 10 to the minus 3. Where am I? So in principle, this goes in k from 0 to infinity. This is a k limit. That means log k, if you think about the power spectrum, most relevant scales are from 10 to the minus 3 megaparsecs, our favorite units, inverse megaparsecs times h. So from 10 to the minus 3. And then this upper limit can be like 10 to the 1 or 10 to the 2. So it's 1 or 2. And here I have a slightly fancy thing where I'm correcting the upper limit for r. So if I have a larger r, I go to lower kmax. But it turns out in Python with this numerical function, it doesn't matter. Even if I just go from 10 to the minus 3 to 10 to the 2 split, I'll get the right answer. The only thing I think I didn't do here is I didn't make sure I have, okay, so I don't think I properly converted from, sorry, because if I say print, maybe somebody can help me even. So I can try to report sigma 8, but it won't be right because I need this conversion from, so here I will want, it's at this r, at r of 8 and z of 0, it's equal to, that's going to be sigma 8, right? And I took square root of this integrated thing. So everything is right, but this I think will be wrong for the reason I mentioned. So let me run this cell. Oh, A of
You need to change the line of DSQ because you are using Z and K before you define inside your function the integrand underscore sigma
yeah,
underscore
defined
SQ.
as I need Z, K, and A. And I
Yes,
do.
the K variable, the local variable K, isn't defined when you
Oh,
call
yes.
in this first line.
Thank you. Excellent. This is a feature where I would have been cheating and knowing this. So I need to have this K first and then this. Thank you very much for your help. Goody. Now we have some more problems. A is still not defined. So A underscore K005. In which line is this? Oh, here. Because it's just, I just defined, I think, plain A in my elsewhere, but it's not going to. So it's 0.52. It's the wrong answer. And it is the wrong answer. And let's see, I think in the chat, I'm already getting help. Yeah, the answer is wrong because of this ln to log. So let's try to figure it out without help here or with just us. So I need the ln k. So this is working in the log k. And so k times, I think here is where, so I need to remind myself here, basic algebra. I always go for my high school. Always go back to your high school fundamentals. So log base 10 of x is equal to ln of x divided by ln of 10, right? So I need, here I have ln, but I think I want d log. So d ln is going to be equal to d log times the natural logarithm of 10. This is ln of 10. Okay. Oof. Okay, right, because I have ln here, but everything else is log base 10. And you know, log base 10 is easier if you think about wave numbers. This is 10 to the minus 3, for example. This is 10 to the 2. So that's convenient here, but the formula has the ln. So I go from, I need the ln, and I replace that by the log times ln of 10. I run this cell now. Okay, people, rejoice. It's a moment to rejoice and be happy because we got sigma 8 of 0.799. So it's about 0.8. We got a sigma 0.8, which turns out to be exactly the kind of value that you should expect with our cosmological parameters. We had angular, we did only assume that BBKS transfer function, which doesn't even have BAO wiggles. And we had a couple of other approximations. We had a, well, the growth function doesn't matter because that's for higher Z. We are still able to get a very, very good answer. This is exactly the kind of answer. So this is a great check. You put in the fiducial best fit cosmological model, and you define all these functions, you calculate familiar quantity, and it's an easy quantity. It's dimensionless, it's ballpark unity, it's coming out exactly the kind of number you like. Okay, so this is our first big victory of the day. Yes, it's ln and log 10. That's, remember yesterday, some small things are giving us a headache. Today, this is gonna be another small thing. It's usually these small things that give you a headache. Okay, so now that it's good, now we have to code up the present sector. And I left some of these tasks for you. So first of all, we want here rho matter at z of 0 plays a role. So we'll need that. And then we'll need this derivative of sigma with respect to mass. So sigma, now our sigma doesn't depend on m, it depends on r, but you can relate m and r. So d sigma dm is going to be like d sigma dr, except m and r related in this way. So this again comes, we can trace this back to simplest model where mass in some volume of radius r is equal to this. It's just the mean mass in that volume. You relate it through. So to do this, therefore, we need a few things. We need rho. Rho is the first thing we need to do. I'm asking you to calculate rho, and I can get us ahead maybe and just fill it out here. So I started us off by saying that this is the kind of, this is going to just be return something. The kind of thing we want is just its critical density. And the key thing is to know which units. Units are going to be our favorite units, which is everything is in H inverse. So H inverse M sun divided by H inverse megaparsecs cubed. This is density, this is mass density, mass per volume, right? And everything is in, even the mass is in units that have a little h. So in those units, this is a number. I say the sum works. So it's that times omega matter times just 1 plus z cubed. Even though it's at any given z, we'll need it at z of 0. Okay, so this is just very simple. It's a rho, mean rho. Okay. Remember, this is not the same business as yesterday. This is just a plain rho, so it only depends on omega matter. And this. Now you have the mass function, and I'm asking you to do a few things. So first of all, the mass function is a function of mass, but sigma is a function of r. So you have to convert, convert from one to the other. And r you get from this formula. So that's 3 times the mass divided by 4 times pi times now that the rho matter. Z is equal to 0 and omega matter. Okay, I divided by that. And I think I got everything. Close 1, close 2, close 3 parentheses to the power of 1/3. Okay, I got R out of M, and then I can feed that corresponding R. They're one-to-one relation. I can feed that R into the sigma. Okay, so this is my sigma that I need in the press sector. In addition to sigma, I need the derivative. And so I take derivative because, again, I do this very simply. What dr should I pick? Well, you are taking derivative, people. So always pick quantity that's some fraction like 0, 1% or 2% of r, right? This is always when you take derivative and don't have much time to think, don't put in an absolute value here. That's a very bad thing to do. Just take 2% or 1%, hopefully it's stable, of r. And then I'm going to be taking for the derivative, I'm going to be using a fancy, this is the kind of thing in C I had to always work much harder. It's so easy in Python. You just call scipy.misc has derivative. You say derivative, blah, 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 from r dr. This means it's a first derivative. And it's passing all the other arguments. It knows to take derivative with respect to the first argument, which is r. So it's going to be taking d sigma dr, and all the other things will be fixed. Okay, so I filled that out for you. Now you want dr dm because in order for this to happen. So basically, first of all, what is d sigma dm? D sigma dm is d sigma dr times dr dm. Again, nothing mysterious happening, is a chain rule. And then I didn't finish this business above, I know. And then the absolute value here, I think this is absolute, but I'm not sure. The absolute value, the d ln sigma d ln m will be m divided by, it's going to be m divided by sigma times, I want absolute value. Remember, that's in the press sector, right? If you go to press sector, there's an absolute value here. This can be negative. So it's m divided by sigma times d sigma dm. Okay. So this is d ln sigma d ln m. I had d sigma dm. That was given in terms of d sigma dr. D sigma dr is just derivative of my function. The remaining thing is what is dr dm for this chain rule. And that can be obtained if you look at this equation, you say ln m goes as 3 ln r, right? Ln m is like 3 ln r. So dr dm is 1/3. I'm trying to do this in my head. Dr dm is 1/3 times r over m, and I hope I got that right. Okay, let me look at the chat. Typo in R, thank you. Thank you, people, for catching typos, by the way. I greatly appreciate it. Typo in R should be Yeah, this is first of all, yes. Thank you, thank you. And then 4, of course, thank you. Ah, excellent. This is takes a village to write computer code. Okay, so what is the value of H naught? Remember, if you go way back, we defined all these global variables. They're not global, actually they are. We are passing them to functions, so they're not global, but we defined the base cosmological parameters here. So H naught is 67. By the way, that's why I was able to get H naught to sigma 8 to agree. These are all Planck type parameters, right? So I chose these wisely. Okay, so I got all that down. Is this part clear? I just had to finagle with a chain rule because it was sigma of R and I needed sigma of M, but M and R are given 1 to 1. All right, so if I run this, hopefully, first of all, nothing will break. And then I'm going to plot the mass function, and I did this for you already. I'm going to plot the mass function in 3 ranges between as a function of mass, d and the LNM as a function of mass at z of as a function of z for 10 to the 13, 10 to the 14, 10 to the 15 solar mass halos. So I have a plot here. I'm going to run it. Hopefully it will run. Okay, so this is my plot. It's actually kind of a nice plot, and I am going to zoom out a little bit. So this is the result of, this is the mass function d and the LNM in the right units. It has dimensions 1 over volume as a function of z between 0, 0, and 5 for 10 to the 13. So this is a group of galaxies. This is a cluster, and this is a ginormous cluster. So first of all, you can see there are many, many more smaller objects and bigger objects. And the other thing you notice that the big objects, they were very few, very, very few at high redshift. And if you go to 10 to the 14ers and 10 to the 15ers, they simply didn't exist at high redshift. So this comes from the hierarchical formation about which Fabian talked about, which is the fact that largest things form last. And if you have a very large, say, cluster of galaxies, it should have formed yesterday. It formed at z of 0.1 or 0.2 or 0.3 or something. At z of 1 already, they're not around. They're simply not around. So biggest things change a lot. But if you go to smaller things, they did exist in the past, not very many, and there are more and more of them. So this is the result of showing, this is showing the Preston-Schechter mass function. The real mass function looks like this. It's just slightly different because, you know, there are more accurate expressions for the mass function. Of course, they are calibrated from numerical simulations these days. So there are some formulae that basically fit numerical simulations. The special thing about this mass function is it's very early. It's almost as old as I, the Preston-Schechter mass function, which is amazing to me to think about. It was that long ago, and it's simple and it's universal, right? And universality holds to pretty good accuracy. Questions about this? Let me look at the chat. Anybody stuck on anything? Python question, I can't help now, or it's going to be tough. R is, that's right. So now for the mass function, we replaced R with M. So now you either have a choice, where's our formula here? You either have a choice of R or M here, and that's your choice. So for example, 8 H-100 megaparsecs correspond to which M? Ballpark 10 to the 14 or whatever it is, right? Depends on the redshift also. So we used to talk about sigma of R, but now we want to talk about sigma of M because that's what enters the mass function. It's sigma of M, right? So as I show you the 3 different masses, they correspond to 3 different radii in this Preston-Schechter picture. But there's no need to talk about R anymore. Now we just talk about the mass function. It's a number of objects at some mass. So now we have, like I said, which is really a research level question that could be part of your project. I have, I don't know, some survey, and just tell me, I have 5,000 square degrees, and I'm covering redshifts between 0 and 1. How many halos above 10 to the 14 should I find? Give me the number. Well, I need the number. So I have d and the LNM is a mass function. And then number density times volume will give me the number, right? So basically I need number density times volume, except I have d and the LNM, so I have to integrate over the LNM over the range from 10 to the 14 to infinity. And then I found it easy to do dv d omega dz because that function is very, very simple. And then I integrate that over d omega dz. So I just have to integrate this thing over all of the denominator stuff, okay? It's just like one big chain rule or whatever it is. It's multiplication, nothing happens there. But now I have to pay attention to these pesky things that have been slowing us from the beginning, right? So first of all, I have this coded up. That was the biggest amount of work. And hopefully this integral I can do. Note a few things. I don't need to run this to infinity. I can stop at 10 to the 16. I can even stop at 10 to the 15 because you know that there is no more objects about 10 to the 15. This thing falls exponentially, right? It's exponentially falling function. So if I go from 10 to the 14, might as well step 10 to the 15. I still have to do this integral. And this integral in omega is trivial because nothing here depends on omega. So I can just multiply by 5,000 square degrees, except those are the wrong units, okay? Unit of angle of solid angle is not square degree, but I can just multiply by omega. I do have to integrate this over z because everything here depends on z. Mass function integrates, and this very strongly depends on z. Okay, so first of all, I have omega survey. And here I'm revealing the answer. It's 5,000 square degrees. There are 4 pi steradians in something like 41,000. Fabian probably remembers this number. Maybe some guys do exact number for number of degrees in the sky. But for all of you school participants, please remember that there are about 42,000 square degrees in the sky. Okay, that's a good number to remember. So you scale that by 4 pi over 42,000 to get this in steradians. Then I'm asking you to fill in the code if you have dv d omega dz. So this is going to be, first of all, I have h naught inverse cubed. And because I want h naught in these units, remember from last time I said one of the more useful numbers to also remember is that h naught inverse, it's 2997.9 in exactly these units, h inverse megaparsecs. Because I want that cubed, I'm going to do that cubed, okay? And then I'm asking you to fill in here for the dv d omega z now. Ah, 42 again, exactly. A lot of things in the universe are revolving around 42. Very good, Esteban, very good. Oh, good. Well, return here this quantity. So this thing is easiest to do as follows. First, I take care of the units. The units of this has h naught inverse cube because this goes as 1 over h naught distance. So this numerator is 1 over h naught squared, and denominator obviously goes as h naught. Here, I'm giving the argument here in words. So this whole thing goes as 1 over h naught cubed times some dimensionless number. So it's h naught inverse cubed times, remember, rz is my dimensional distance. It's z omega matter omega k. And by the way, this is amazing that this thing is filling it out for me. It's incredible for this environment is times, and then I need, and I need that squared. And then I need 1 over this, what we call E of z sometimes, the h of z without h naught. But that we defined above, that was that distance, this integrand that depended on z omega matter omega k. Remember this integrand? That was 1 over square root of that stuff, right? So it's r squared divided by, it's 1 over h without h naught, and then h naught I took care of. And the most important thing is I got units right. All right, so now pedestrian way, go to z max of 1, make 10 steps. I'm going to be integrating slowly by hand. So it's going to be, I'm going to get array of z array. And then I'm going to have 20 steps in mass. You can check that it matters or not. As I said, I don't have to go to infinity. I can go from 10 to the 14 to 10 to the 15. It's enough. I define that array. Then I need to integrate. I'm going to integrate in here. I'm going to have, first of all, dv d omega z. I see. So this was kind of the key line. I filled it out for you already. I see. So that expression said, the key part was the mass function, right? Mass function is here times dv d omega dz, which is defined above, times dz dlnm times omega survey. That's not a d anything, right? It's just multiplied by that number. So I'm gonna integrate this. We have a double integral, right? We need an integrate in z and m. This is not an integral anymore. Integral in z is here. I'm gonna just have this temporary, I'm gonna sum the temporary variable. Temporary is a list of these terms for each value of z, right? So I have for each of 10 z's, I have this and I sum it up. That's the first integral. And then integral over dl and m is kind of pedestrian. I could have done it more fancy. I'm gonna have m, I need to fill this out. So m is 10 to the power of log 10 m array of I, right? Because for the ith element, this is going to be m is going to be, this is an array of log 10m, so I have m, I need m as well. And then the eternal conversion, don't remember the conversion. I kind of like to write the integral this way because here I can see exactly what I'm integrating. I need the ln I have step here, the way I subdivided the space of masses, I subdivided in log. And so this is as a default, see, I did it 10 to the 14 to 10 to the 15, right? This is the log m is that. So I convert from the log m to the ln m by multiplying by this. This is the kind of detail that can catch you. But if I do that, if I've done all that correctly, I realize this is kind of a lot, but okay. So, so something is, was it square parentheses maybe? Let's hope. Oh, thank you, Natalie, thank you. AK005 was just a, so this is a kind of when you're doing programming, sometimes these definitions, when you define a function, say, here's my function, you can call these anything. They're just for internal use, right? So I could have called them any names, A, B, C, D, E. Of course, they're terrible. There'll be terrible names. But so they're any names in definition. The important thing is when you pass the variables to use the variables defined above. And if you see what I defined above, it just happens I used all the same names, but this one I didn't call A.005. I just called it A. So sorry, I maybe I should have called them all different names here than in the function definitions. But basically, I do need to call, if I'm calling out these variables, I do need to eventually call them by these names. So I only have A. And it took a while for that code to run. Why? Because it's doing multiple integration. Already this, see, I didn't do anything to speed it up. I was just, sigma is an integral. Then I guess the mass function is not an integral. And then I'm integrating two more. So I have at least triple integral. I have one in sigma and two in here. And so it takes a while. I get the answer. If you do that correctly, you have 33,000 clusters above mass 10 to the 14. And just for fun, I'm asking you now do the same, but what happens in Einstein de Sitter universe? So this is one of the early ways people try to figure out the geometry of the universe and what is omega matter. They realized that the number of clusters would be very different in a low matter density universe like the one we live in, and the one that was originally the most popular, like given by the simplest model, just matter. So to do that, I can just use the same piece of code. I don't need to go back and fix it because everything above this is a function, right? So this is calling mass function, which is calling sigma, which is calling P of K, but they're just one thing calling another. They are obeying command of what omega matter I plant in. So all I need to do here is say omega matter is 1. That's the only. Change to new Cosmo model. Omega matter is 1. And then it's still going to remain flat because I have upstairs that omega curvature is 0. So it'll know that it's still flat, but omega matter is 1. It's just going to call this, and I'm going to run it again. So remember, that was 33,000 in lambda CDM. And in omega matter 1, we have to wait for the answer. it's doing this triple integral completely inefficiently. So you realize if you're going to do research with this, you have to speed up your code. And maybe if we have time, we'll talk about basic ways to speed up, to fundamentally speed up, not to go to a faster machine, to really fundamentally speed up the code. We'll talk about that. But for now, we are expecting 810,000 clusters. So we went from 33,000 to 800,000 clusters. So there's many, 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 many more clusters in another cosmological model. And the reason is, if you think about these mass functions, if you have more matter in the universe, you get a head start at the formation of these large objects. So you really get many more at late times. So this is really an amazing illustration of why galaxy clusters were one of the early probes that indicated that we potentially live in a low matter density universe. There was an important paper by Simon White and collaborators in the early 90s. There were papers by other people which indicated this. And you can see the power of that argument. You can see from our calculation. You get more than 20 times as many in a cosmological model where it's all matter. So yeah, this is not a simulation, Esteban. So you mean in a fancier calculation, say. So in a simulation, you don't do the integrals, right? You do integrals when you do theory. You do the following. I'll just mention it in one sentence, and that's a topic. You do a thing called tabulating. So this is, again, a simple-minded way to do things. The sigma of r is a function. And right now we are spending a lot of effort. We have this routine here that's doing a lot of many times is this routine run. And this integral here, this integral, is being done many times as we call these things calling things. This integral is being, but this is a tough integral to do. It takes a while. So instead of doing this integral a billion times, I don't know how many times you're doing it, why don't we do this integral 100 times at different values of r, maybe even different values of z, and tabulate, remember, interpolate, remember those values, and then make a table of sigma as a function of r, or maybe even sigma as a function of z of r. And then you interpolate within the table. This is a process called interpolating or tabulating, and that can dramatically speed up your code, because instead of doing an integral, I don't know, a billion times, you do it 100 times or 1,000 times, and then you just call up the function to look up the values, which is very fast. So that's a key speeding device to make these routines faster. You can do that for distance, for sigma of r, and for many other functions. Yeah, that's, I thought I was going to maybe spend more time in talking about tabulating, but we got through this, and I'm glad I at least got to mention it. I think here we're at a good point to maybe stop. I don't know if there are any other questions, or whether the organizers would like to say something, and maybe I'll leave this last function here. But back to you, organizers.
I guess it's up to you guys. Let's see if we have questions. If people want to open up, go back to something that was done, it's really up to you. We have we can have a bit more time, right, Rogério? I think it's okay.
Yeah, sure. So maybe I can, I was talking a lot and I realized I was going to get some pace. So let me maybe, oh, right. They're meeting, yes, Nico, thank you. You're meeting for discussion. See if there are any verbal questions from people. And I guess I'll stop sharing at this point. If there are any want to speak up and ask a question, we can do quick questions, quick answers, or anything.
I guess people have more like practical questions that they are there was a lot of activity there in the chat. And I think, so the students are meeting for exercise discussions after this is over. So they will also have the chance to figure out some of the questions about Python and so on. But we do have a question.
So first of all, Sebastian had a very good question there, and I think it's being answered by Guanhao, which is that he thought exactly critical density does depend on redshift, period. The one in that formula is critical density today, a rho crit. So it should have been, I gave it the wrong name. I should have called it rho crit 0. Because if you take rho crit 0, that thing you multiply by 1 plus z cubed, etc., that'll give you at any given z. So that was really critical density today in that formula. Random catalogs, you mean for the Landisla estimator? I assume, Ariana, you are referring way back to Landisla estimator, because we didn't have any random catalogs in this coding exercise. If that's what you mean, that's simple. All you need to do is take, volume on your computer and call the random function, and put randomly points in 3D, just like you would pick random values between 0 and 1. You would imagine doing that in 3D, so between 0 and 1 and 0 and 1 and 0 and 1, and maybe not 0 and 1, but in some box. So you literally randomly pick locations in a volume, literally. And then what you're faced with next when you're evaluating that estimator, is somebody already mentioned, is n-squared operation. So you're finding pairs. If you have 100 million squared is a lot to check for. So there might be ways to speed that up.
Okay. Well, I guess we are 20 minutes after the time, so people seem to be satisfied.
Yes, I don't like going over normally. I'm sorry about that, but
No. I meant lots of questions were asked during the lecture.
Yeah, the nature of this is such that when you have, again, especially since I didn't have the benefit of looking at my own solutions,
right?
So a little bit like student on the blackboard, not knowing, but we got it, and It's a good thing to maybe spend some extra minutes to get to the code.
The students should know that we're always looking at their faces to see what's going on, if we are going overboard or something. And in this situation, we don't have the camera, so Dragan is having to regard on me to call on me and Huterer to get this feedback. But I'm sure that the students are asking any questions that they want. All right, guys. So if we don't have any more questions, we only have people giving reactions. So I guess we can close for now. And thanks everybody. Thanks Dragan a lot. And
thank you, ladies and gentlemen. Thank you, Raul. Thanks all. We'll see you again tomorrow, and feel free to ask questions on Slack. I'll be answering certainly tomorrow.
Excellent. All right.
Okay.
Ciao, everybody.